Alright, let's dive into something mind-bending today. Have you ever stopped to think about how a beam of light can cross the entire universe in what feels like no time at all? I mean, it's a statement that sounds almost poetic, but it's rooted in some of the most profound physics we know. Personally, I think this is one of those ideas that makes you question everything you thought you knew about time and space. What makes this really interesting is that it's not just a theoretical concept, it's something we can actually measure and observe. But let's break it down, because there's so much more here than meets the eye. First off, let's talk about photons. These tiny particles of light can travel 1 billion light-years, a distance so vast it's hard to even comprehend, and yet, from their perspective, no time has passed. Zero. Nada. It's like they're on a cosmic sprint, but their stopwatch never starts. In my opinion, this is where things get truly fascinating. We're so used to thinking of time as this universal clock ticking away for everyone equally, but here's the universe saying, not so fast. Time isn't a one-size-fits-all concept. It's relative, and it depends on how fast you're moving, where you are, and the path you're taking through spacetime. One thing that immediately stands out is how counterintuitive this is. If you take a step back and think about it, it's almost like the universe is playing by its own rules, and we're just trying to catch up. Now, let's talk about time dilation, because this is where things get even more mind-boggling. Imagine two identical atomic clocks synchronized, side by side. You take one, put it on a fast aircraft, and send it on a trip around the world. When it comes back, guess what? It's behind. The traveling clock shows less time has passed compared to the one that stayed put. What many people don't realize is that this isn't just a theoretical prediction, it's been proven. Back in 1971, physicists Joseph Haefel and Richard Keating did exactly this experiment, and the results matched Einstein's predictions perfectly. This raises a deeper question. If time can slow down for something moving fast, what does that mean for us? Are we all experiencing time differently depending on our speed and location? From my perspective, this is where physics starts to feel almost philosophical. But let's zoom out for a second. What this really suggests is that light is the ultimate rule breaker. At everyday speeds, motion works like we expect. Throw a ball from a moving car, and its speed adds to the car's speed. But light refuses to play by those rules. No matter how fast you're moving, light always travels at the same speed, about 299,792 kilometers per second. Einstein made this the cornerstone of special relativity in 1905, and it's a game changer. If everyone measures the same speed of light, it means that observers moving relative to each other can't agree on both distance and time. Those measurements have to adjust to keep light speed constant. A detail I find fascinating is how this led Hermann Minkowski to describe space and time as a single, four-dimensional structure called spacetime. It's not just space over here and time over there, they're intertwined. Now, let's visualize this with a light clock. Picture two mirrors with a pulse of light bouncing between them. Each round trip is a tick. When the clock is at rest, the light goes straight up and down. But if the clock is moving horizontally, the light takes a diagonal path because the mirrors are sliding sideways. That diagonal path is longer, but since the speed of light can't change, it takes more time to complete each trip. The moving clock ticks slower from the perspective of a stationary observer. What makes this really interesting is how it ties back to the idea of spacetime. The geometry of spacetime itself is dictating how time passes. It's not just about speed, it's about the path you're taking through this four-dimensional fabric. And here's where it gets even crazier. As you approach the speed of light, time dilation becomes extreme. At 90% of light speed, a moving clock runs at about 43% of a stationary clock's rate. At 99.9%, it's down to just 4.5%. As speed approaches light speed, time dilation approaches infinity. Time, for all intents and purposes, stops. This is why a photon, traveling at the speed of light, experiences zero time. It's not that the photon is aware of this, it's a mathematical consequence of the physics. But if you take a step back and think about it, it's almost like the universe is saying, you can't outrun me. Light is the ultimate speed limit, and time is the price you pay for trying to reach it. Now, let's bring this back to the real world. GPS satellites, for example, rely on these principles. They're moving fast and are in weaker gravity, which affects their clocks. Without accounting for time dilation, GPS would be useless within hours. So, this isn't just abstract physics, it's technology we use every day. What this really suggests is that relativity isn't just a theory, it's the framework that underpins our modern world. And yet, it still feels so alien. Time isn't universal, it's personal, shaped by motion and gravity. There's no single clock ticking away for the entire universe. Each object, each observer, has their own version of time. So, where does this leave us? Personally, I think it leaves us with more questions than answers. If a photon can cross the universe in no time, what does that mean for our understanding of distance and duration? If time is so relative, how can we ever truly synchronize our experiences? And if light marks the boundary of cause and effect, what lies beyond that boundary? These are the kinds of questions that keep me up at night. What makes this really interesting is that it's not just about physics, it's about how we perceive reality itself. It's a reminder that the universe is far stranger and more wondrous than we could ever imagine. So, here's my closing thought. The next time you look up at the stars, remember that the light you're seeing has traveled across the cosmos, and for that light, no time has passed. It's a journey that spans billions of years for us, but for the photon, it's instantaneous. It's a beautiful, mind-bending paradox that challenges everything we think we know. And that, my friends, is what makes physics so incredible. What do you think? Does this change how you view time and space? Let me know in the comments below.